Okay, thank you. I'm back, and thanks for the flexibility of shuffling slots here since I have other constraints tomorrow. And Jayanta asked me to, I guess, give my thoughts on where things are headed. I think we've heard a lot about the exciting developments over the past years and decades of how we got here. And I think different people probably have different views of which way this could go. So I'm going to speculate. This is my personal speculation of what directions you can think about and what might be interesting to do. Just to say the obvious probably is that you can go into different directions, different metrics of what's interesting and what's not. So you could try to get as much sky as possible. And the limit is 4 pi steradians. And obviously, you're not going to see that from a single spot on the Earth. And transient means, well, I think what we have in mind here is transients where you don't know where the next one is going to go off. So you've got to be looking everywhere. And everywhere means you've got to have multiple telescopes across the Earth if you really want to catch every single one. So with that goal, there are in fact a number of initiatives ongoing to cover the planet with enough stations that you will catch every event if it's bright enough. And anyway, that's one obvious direction. Another obvious thing you can try to do is to find the faintest of transients. So there, what you want is the biggest collecting area imaginable. I thought it was missed on our SKA roadmap that the most sensitive thing existing is fast in terms of total collecting area, or SCFD. And that's going to see the faintest events that you could imagine. And then there's yet a third metric, which is neither of these, but the maximum number of events. Okay, you want to optimize. I just want to see the most number of events, and you say, what would I do to achieve that? And I think in each of these categories, there's some obvious existing or about to exist experiments. I should have listed CHIME in the existing category, which is just the obvious. It leads the number of FRBs by a large factor over everything else. Not because it has the widest view, it is neither the widest view nor is it the biggest, but it has the highest event rate because it sees the most volume in the universe. And then there's another metric. I just want to mention that at longer timescales, I'll get to that in a second, CHIME has not actually found many longer duration events. And not because it doesn't have sensitivity. Obviously, you'd think with this much sky and this much sensitivity, if it does, 100 times better on FRBs than any other telescope, why doesn't it do 100 times better on other transients? And I'll try to get to that, and it's work in progress, mostly confusion in the sky, that there are all kinds of things that happen that you have to worry about. Just one reminder, so I find that there are 2 types of audiences responses I get. I think it's kind of obvious that an object will appear brighter if it's closer. No brainer. Okay? The same object, I put it nearer, it's going to appear brighter. The converse, if I see a bright object, is it likely to be nearer? And surprisingly, there are many people who say, oh, it's not obvious and it's unlikely to be true. So this just seems surprising that this is even a debate. Okay, clearly an object will appear brighter if near. So conversely, bright objects, at least on average, will be nearer. I mean, there can be an exception, but statistically, how can this not be true? I think people may be misled by our textbooks that there's an exception to this if things are at high redshift and are evolving. There are quasars and GRBs and other things. There are a few spectacular candidates, objects for which it happens to be not true, but that's a rare exception and only true at very high redshifts when they evolve rapidly. For FRBs, that's guaranteed not to be the case because they are at redshifts, almost all of them are redshift less than 1. So you don't have to worry about it. So the obvious has to be true. Just to say the obvious, okay? It doesn't depend on populations, does not depend on luminosity functions. Very simple story, just to fill in. Meaning the wide field ones, I hope with this thing, the obvious, if you want to identify a counterpart, if you want to learn about where it is, the environment, you've got to find the nearest one. And the nearest one will be bright. I think that's safe. Okay, so the white ones are good. Each of these categories has its own own science applications, depending on what you find most important. So it's hard to compare them. There's not a single metric, but that's roughly, that's the things I thought about one could try to optimize. There was an article in Science News written by Dennis Normil, published a few months ago, and he was kind enough to put a picture of bursts on his article. And he was actually, I was certainly confused by the questions he asked me, which he said, oh, he's writing an article about the upcoming wide area aperture arrays that search for FRBs and other objects. Okay, that's in his article. And so he called me up and he says, oh, can you give me a date of when you're going to turn on operations? And he actually asked me 2 weeks before that date. And I thought it's too dangerous to give a concrete date. So I said, look, I'm not going to commit myself. I'm going to, I'm going to play it safe. I'm not going to give you a date on when it happens. Obviously, our other colleagues are very confident and actually gave him a date on when they're going to start science operations. I'm not sure what that word actually meant, but I thought, oh, in my mind, it means fighting FRBs. So it turns out a week later, I emailed him and I told him, actually, you found an FRB. So maybe I could say we have started science operation, but it was too late. We missed the cutoff date of the article. So burst was, of course, is the last one according to this table to find something, but actually is the first to have found something. So that means, it's difficult when when a reporter emails you, you have to keep in mind that he emails multiple people and different people may have a different interpretation of what this question means. But anyway, let me go through. It's an exciting time that there are quite a number of experiments coming online. So this idea is clearly an idea of the time today, and this is happening. So just to remind, I don't know how, we did not have a CHASM talks in this meeting, did we? No, there's no talk. Okay, so in that case, I'm not wasting time this is just from Liam's website. By the way, Liam, I'm proud to say, is a former student of mine who's now building a competing experiment to me. This is a good student, right? Who does things, who can compete with you. And these are, again, dipoles that operate in a very similar frequency range as burst, and this is about to start operations, he says fall. So we've got 2 more months to go. There's another one, again, here's another student of mine, Dongzi. Okay, so all my students are building a competing experiment. This is great. Okay, I just need to have more students, and then we will solve this problem of having a telescope everywhere on the planet. I just need to take more students from all over the world, and here we go. And now this student, both students, by the way, are fairly, what do you call it, confidential. That I emailed them. Oh, I read in an article. I read that you're building an experiment. Can you tell me more about it? And they both said no. So this is all very secretive. So my information comes from just this article. I'm afraid I have no more information than you do, which is fine. No, that's what your students should be doing. They should be going on and building bigger and better things than you have done yourself. Perfect. So this is yet another, I was counting, if you count how many elements, I think I counted 150 some elements. But this is counting this image, okay? I could not find any information on how this would work, which is actually a reasonable collecting area to see events. And this also has outrigger stations. So the commonality is that you want to not only detect them, you want to actually localize them as well. And this is all happening. It's an exciting time. Now, these are all things that are happening, and it's just a matter of waiting anywhere between weeks to months before we'll have multiple of these aperture arrays at multiple points across the world that are going to, I think so this question of are we going to see the bright events anywhere in the sky? I think the answer is yeah, we're getting there. We're actually getting this a good fraction of the sky with multiple stations across the world. Now, and as some of you know, I have no shortage of dreaming big. So if you've built 2 physics elements, why not build them more? And here are some the basic. And now I'm afraid in the radio world, many people don't like this acronym because the people who coined it are not radio astronomers. but I think that's okay. The FFTT, the Fast Fourier Transform Telescope, allows you, of course, to, with only n log n cost, form all beams in the sky all the time. So this, I was disappointed that when I was at an SKA meeting 20 years ago when this came about, the SKA expert says, we hate this. We're not going to detain this notion, and we will only form a small number of beams at n squared beamforming cost. So even the aperture versions of SKA are not planning to do the whole sky all the time. Was not up for discussion. I think that's unfortunate because that's a big investment, a big opportunity. Even the aperture array, which is not under construction, but the idea is the same, just have a large number of dipoles see the whole sky all the time. No, they don't want to see the whole sky all the time. They only because if to sell this, I think politically, in order to charge people money to pay for it, they've got to get something for it, like looking at the point you want to look. So that's my feeling as to why you don't want to see the whole sky, because then you can't charge extra money to look somewhere else. But that's okay. It is certainly a design which is not planning to see the whole sky, but costs a lot of money. And maybe it'll happen someday. And maybe by the time it happens, people will get to the senses and look at the whole sky, might as well. Others, of course, we are ambitious to we have identified a site in Taiwan to build a larger version of 8,000 elements. Liam is certainly ambitious. In his paper, he talks about a 25,000 element version. Okay, this is good, and you want your students to be more ambitious than yourself. That's exactly what the world needs. And the Keith Bannister at CSIRO mentioned Casado. I forgot. It was also tens. If anybody remembers that, he also had in mind something at least as big as the other two. So I think there's no shortage of. And these are they actually have in mind a design and a place, and all they need is some more money. Okay, so these are all things that I'm optimistic that certainly some of these are going forward in the near future. So I think this is all great news. We will have many events in a very diverse. We're going to get many more. So we're just at the very beginning of this new field. I think that is a safe statement. Now, to dream even bigger, beyond what's already designed, finished, and on the drawing board, I like to think further in the future. It's kind of strange, but as I get older, I think further in the future. It should be the other way around. When you're young, so my students are doing the right thing. But anyways, I guess I'm still young at heart, want to dream. So if you only look at if you're really ambitious and you build large numbers of them, how big could you realistically build one, and perhaps even have somebody pay for it? So if you look around right now, the efficiency of our digitizers is terrible. Okay, an FPGA is something that's meant to do everything for everyone, and is obviously very inefficient. If you have a custom chip, an ASIC, like all computers, I'm sure every one of your computers has a gigabit Ethernet port, which will sample much more than what we need for an antenna sample. At almost no cost. That part of the ASIC costs a few cents and draws at best 2 watts. Your laptop Ethernet port, this takes, this laptop doesn't have that much energy. They can't spend 50 watts on your Ethernet port. So this is in mass production on an ASIC, actually very power efficient. But even these FPGAs that we use, they cost some money today. It doesn't cost them it doesn't cost Xilinx very much to make a chip. So with competition, it's going to come down. So if you think of, if you want to think for the next generation, in a few years, this presumably will because their cost is very low. They can keep competing this down, even if technology does not improve, even if chips, don't get any cheaper. This product competition will drive it down. And same with front end. There's nothing actually expensive other than the design and the low quantity. In large production quantities, these analog, like on your cell phone, the whole analog circuitry with phase beamformers and everything, or in the Wi-Fi station. I don't see one here, but nowadays often you see these Wi-Fi antennas 6x6 has 6 antennas with a beamformer inside. They cost very little. These can be mass produced. So if you have the goal of building 10 million. Okay, this is something where you kind of are limited by these asymptotic scaling costs. So, you know, I'm thinking by the time you can actually finish building this, this is the kind of scale that is manageable on a project size. It's much cheaper than something like SKA or NGVLA in comparison. I was visiting Tony Beasley last week. He says, oh, he's very positive. He's going to find $4 billion for the NGVLA. So this is only 5% of the cost of a big project. So this is something that will fit in a custom designed kind of category. So then you can ask, oh, and then where are we? So how do we increase the number of things? This is a bit out of order. But as that CHIME actually the sensitivity drops to much worse than radiometer beyond about 10 milliseconds because the system is unstable, there's interference, there are other things. So there's actually very few events longer than that, not because they're not there, but because CHIME is very inefficient, and we know that from injections. So in fact, I think the current interpretation is that we're probably missing the majority of FRBs because there are many more FRBs that are scattered. And from high frequencies, if you extrapolate the scattering, we should have many more than we see, but we don't see them, and that's consistent with our inefficiency. So you can try to. In fact, Sriharsh was working on it until he went into a different universe. But in CHIME, we have another two scientists that are leading a project to stabilize our system on all time scales, at least in Stokes V. Stokes V is much easier. You have almost all Stokes V sources on the sky are coherent transient sources. That's the good news. So in that space, you don't have contamination. There's no confusion because in a small aperture, if you look down at the sub-millijansky level, there are millions of sources on the sky. Some of them are varying on their own, and it's actually very difficult not to mention your system is varying. But in Stokes V, on a linearly polarized feed, it's actually very, very stable. So we're hopeful that we can actually see, they're now working on this pipeline to actually do CHIME. So we hope that the longer period window will be opened up in the near future. Unfortunately, the Stokes V is only recorded at 10-second cadence in CHIME. So at 10 seconds and longer, CHIME will see Stokes V, but between 10 milliseconds and 10 seconds, it's unclear what can be done to increase. So there is a window of opportunity to that is currently unspoken for. And I mentioned there are various other trade-offs. Now, science, you say, well, okay, why would you want to do that? Who needs more FRBs or more of anything? And just to put a bit of context to this, with 10 million elements, so 10 million square meters, I'm going to call it 10 square kilometers. So this is 10 square kilometers, which is about 100 times bigger than the SKA collecting area, for 10% of the price. So this is a good deal, right? You can, if that's all you want, if that's your goal of doing, this is obviously, SKA has a very different goal in mind. This doesn't make beautiful images of radio jets. This is a very, focused experiment to see transients, but only costs a very small fraction and has huge sensitivity. 10 to 10 have a lot of FRBs. This is, you're basically seeing every FRB in the Hubble volume. So you see, this is, you can say, well, I mentioned microlensing by stars. You're going to get, 1 in 1,000 is lensed. You're going to get 10 million lensed stars. You're going to measure the stellar population of every type of galaxy, everywhere within every galaxy, in every subpopulation. You'll know, the stellar mass function. You know the stellar planetary mass function in all galaxies of all types. If you want to know elliptical galaxies, how many Earth mass planets, you just know. Okay, I don't know if anybody cares about how many Earth-like planets are at an Earth radius in a elliptical galaxy, but you'll just know the answer anyways. This is just so many. You have so many of them, and again, 1 in 1,000 of my stars has a planet microlens as well. So you're going to have thousands of planets, extragalactic planets, cosmological distance planets. You can do macrolensing, you can measure, all these things that before you might, that all these questions in the textbooks when I was a student, you go and Binny Tremaine and you say, oh, lots of things you don't know. Well, you can just measure them. There's, I don't need to explain to this audience, anything that anybody's ever talked about in the transient world. You'll just see, mountains of them. Statistics is not an issue. pulsars. You will just see pulsars in other galaxies nearby. They've got 10 square kilometers of collecting area. You can do a pull timing array. You know, our galaxy is not the limit. There are many galaxies in our universe. There are many pulsars. There are many millisecond pulsars in our universe. You know, you can be very ambitious. So if you really want to make high resolution maps of the gravitational wave sky, there is no limit. I mean, you know, this is a bit ambitious, but not. But this is very cheap compared to the actual projects people are spending a lot of time and energy on. As I mentioned, you know, NGVLA. This is almost nothing compared to big projects. And even just from the redshift to 20 centimeter line, you get tens of 100 millions just galaxies by the redshift at high redshift. You just map out the position structure of the universe at high redshift. So this is all, you know. Jayanta asks, what could we be dreaming about? Well, this is what you can do to be ambitious. So, stepping back a little bit to today, and I think to people that might be of interest to people in this room or online, they are in these various directions. So the short term, as we saw, there are these aperture arrays coming online. We're starting to fill up some chunk of the Earth's viewable sky. I think we're maybe still only at we're definitely less than half, even after these immediate projects come online. So as we see, you know, when California and China actually has the same sky as Taiwan. But in Europe, there's a talk about building things, but there's still a lot of sky that's unspoken for. So if there is interest, you know, every scale is actually helpful. So this is an opportunity for new collaborations, if anyone is interested in deploying an array. And you want two types of things. You want main stations that are sensitive and outrigger stations to localize. And the more the merrier. So this is an exercise, as I was explaining. If you want to do VLBI, the more the better. They don't need to be that large in cross correlation because there's a collective effect. So here's an opportunity for anyone who, you know, wants to try something out. You can join a global network of transient, including VLBI initiatives. Again, as I mentioned, VLBI not just for localization, but to resolve scintillation. You know, we've heard scintillation. We hear it a lot, which is great. It's great to see that scintillation is crossing the awareness threshold. A few years ago, the word scintillation was almost never heard at any conference. It was at best an annoyance for the time people would at most complain about it. And I think it's only in the last couple of years, you know, that we hear, even this morning, it was a pleasure to hear that the scintillation is an actively thought about topic now. And VLBI is the ultimate tool that you'll just know where everything is happening, and you can use it as a very precise tool. And that's why this network was very powerful. And I don't know, maybe we need an acronym for this next generation. I coined it the 10 square kilometer array. And here's a chance of, you know, thinking far and thinking big. Thank you.
Thanks, Bailey. It was really interesting. And any thought or any comments that you want to give? Yeah. Oh, yeah.
That's very interesting and encouraging. Thank you. One of the slides you mentioned about some 10 millisecond instability coming from on the system that is affecting some. So in one of the slides.
About which?
About instabilities.
Or instability.
Yeah, that's one. Yeah.
You mean why it's unstable on longer time scales? Well, the phenomenon is just that you look at the power on a total beam, and you want to look for, you know, is the power going up? That's how I want to find FRB or find any transient. But what you find is the power fluctuates. And the thought is you have 1 over F noise, probably gain variations. And this is very sensitive, right? This is, you're phasing 2000 LNAs. And when you do that, if you sum up a bunch of 1 over F noises, then your baseline varies and that dominates your noise. You're no longer thermally limited. That's the current interpretation.
A question is related to, I mean, curious question on the RF-SOC costs you had put.
SOC, RF-SOC cost, yeah.
Is it really $100 per input?
Okay, so in our current burst, this is actually based on our current design, where the way you get there is you mix. So these have, if you have 16 inputs and you're sampling it at 2 gigahertz or 1.6 gigahertz, you find that, oh, but there's actually more bandwidth than I need. So they're actually not well matched at low frequency. So, but if instead I mix many channels into one, then the cost per digitized channel, that's what I'm saying, per multiplexed digital input is one. If you put 64 inputs into one, it gets cheaper.
Only doing some 500 megahertz band, I think.
If you have, let's say, 200 megahertz, if you only care about 200 megahertz.
16 of them.
That's right. So 200 gives you about a 50% bandwidth. And again, if the wider band is very inefficient in terms of cost, because you've got to space your receivers, half a lambda. So at high frequencies, you actually have no collecting area, but you're paying a lot of money. So that's why that's why Chasm and the next generation of bursts, we're actually reducing our bandwidths to get more elements.
Or on the CASM 25,000.
So about which?
CASM 45,000.
This one?
No. The 25,000 one.
25,000. Yeah. So that's all based on reading, drafts, papers or preprints or papers that they post, and their description of it changes every paper. So I'm not sure that there is that anyone has a pinpointable spec. At the time, they were talking about wideband, but I think nowadays everybody is shrinking their intended bandwidth. And because this 25,000 is not actually funded, I suspect there'll be many more changes before that actually gets finished. So I think these specs are probably the closest we can work with, and just multiply this number by 100.
Okay. Yeah. When some of us were talking about the upcoming DSA 2000 will provide 10 to the 5 FRBs in the future. And we were talking about what science could be if we have that kinds of FRBs, but Wesley was mentioning 10 to the 10 FRBs in the future. Then I think the science that we can use for do with those kind of FRBs with whatever we want in astrophysics would be really amazing. If we have with ongoing projects and upcoming projects, and also the proposed one in the future. So we have still 1 more days for tomorrow, but yeah, that's probably to any.
There's one question that's wanting to ask about is global collaboration on the trigger.
But how to do collaboration on these outriggers, what I have in mind here. So for example, Sujin and I are going to visit Garibat Noor. It's kind of close to here. And we're building a burst outrigger here. So that's a baseline of how many kilometers? 3,000. 4,000 kilometers from here to Taiwan, to the VLBI right down nearby. And of course, you want more of them. You want to have more UV coverage. So I think that's a great opportunity. You want more such stations.
That's within the burst collaboration. But if it is outside, how about sharing triggers as a global availability for other monitoring stations?
Yeah, of course. I think we all want to maximize science, and we're happy to share whatever makes scientific sense and is actually manageable. Obviously, it's a logistical limit as well of what can be implemented, but definitely.
Thank you.
Thank you. So I think maybe we can go for the lunch, and I apologize for the delay. And let's thank to Wesley for really interesting and amazing talks.